In this video, we're going to discuss instantaneous rate of change. So rate of change at an instant, at any single particular point where we're interested in. So the issue so far is that the average rate of change computes the rate of change between two given points some distance apart. So let's draw a sketch of the situation as we have seen it so far and discuss how we can adjust our methods to actually produce something that we can specify at any given point in time. So let's say this is my function, some f of x here, and I am interested in the rate of change of this function at the point x. So that means that I would like to know how fast is the function growing or decreasing right at this point x. The average allows us to compute it between the different 2 points. So I have to pick some other point on my function. I have to construct a secant line, and the average rate of change will represent the slope of that line. Now, of course, these 2 points are pretty far apart, and my line doesn't quite look like the function. So I would like my secant line here to actually mimic the function a little bit better, which means that I can move this point, the second point that I have to pick, closer to x. So if I move it, for example, here, I can see that my secant line is going to be sort of a little bit better, a little bit closer to describing the function that it's trying to approximate. I can move it a little bit closer still, and it's going to be a little bit better still. So these are all called secant lines. Now, if I keep moving it closer and closer and closer to my original point, at some point, I will actually be so close to the point x with my second endpoint that I'm essentially going to be right on top of it. And that's where I'm going to produce the line that is the most accurate in terms of the rate of change that happens at that point. Essentially, the 2 endpoints are moved so close together that they're on top of each other, and I'm computing the slope of the line between the 2 points that are infinitely close together. This will be what we call a tangent line. Now, the names secant and tangent actually come from Greek. Secant means to cross, and we can see that all of these pink lines actually cross our function twice, right? At the point where I'm interested in and at some other point. A tangent in Greek means to touch, and indeed this line only touches my actual function. Now we can see how this works in practice. So let's take a look at this Desmo here. So the purple point at the bottom here, let's say this is my point of interest. This is where I want to calculate the instantaneous rate of change. So I would like to know how fast the function is growing at that purple point. I start off with this green point up here and compute the average between the two. But again, these are quite the ways apart. So what I can do is I can move the green point a little bit closer and produce the actual secant line that a little bit better represents what happens at the purple point. I can move it a little closer still, and now I can see that my green line is even closer to my red parabola than before. So this is another really important property of what's happening. If I move my green point to the original position, I can notice that the green secant line doesn't quite look like my red parabola that it is trying to imitate. But the closer the green point moves to the purple point, the closer the secant or the green line looks like the actual parabola, the red line, right? So when I'm already here, I can see that on this zoom level, they are almost identical. And then finally, if I move them to be right on top of each other, they're actually going to merge into one singular tangent line. Now, what does that mean in terms of applications? Let's go back to our COVID-19 vaccination application. Remember that the second part of the question asked to describe what actually happens over time in terms of vaccination rates. Are they growing? Are they slowing down? Are they continuously growing but at about the same speed? So remember what we did was we looked at a 3-month period. So starting with December 14th and March 14th. So we ended up somewhere here, and the average that we computed corresponded to the slope of this line. Now, of course, you can see that this line doesn't quite mimic the curve that it's actually the vaccination curve underneath it. So if I took points closer to each other and connected them, I would be able to better represent my actual vaccination curve with these specific lines. And in particular, if I am looking for where the vaccinations are growing the fastest, what I can do is pick any particular point on the actual curve and draw a tangent line to it, as opposed to thinking about picking 2 points some distance apart and sketching a secant line, right? For any particular point, I can now think about drawing tangent lines. So something that is only touching the curve at that point and yet mimics its behavior the best of all the available secant lines. In terms of the general setup, let's think about any given function. So let's call it f of x here. So my blue function here is f of x. My red line here is the standard secant line that we've been drawing all along. The slope can be computed as rise over run. So in order for us to do that, we need to label a few more things on the diagram. So let's say that the point at which I am interested in average and instantaneous rate of change is this left point on the curve right here. Let's call it x. Now, because I have to compute the slope of a secant line and I have to start with the average, I need to introduce a second point some distance away from x. Now, I can call it x1 or anything else I want, but the idea is that this point is going to be moving closer and closer to x, and so it's better to describe this point in terms of its distance away from x. So I'm going to say that it's going to be distance h away from x, which means that if this point has x coordinate x, this point has the coordinate x plus h. Now, that's of course in terms of the x coordinates. What about the actual y coordinates? So if I look at where these points land on the y-axis, let's label the axes here, what I see is, of course, my function is f of x. So if this is x, this point, the y-coordinate, is going to be simply f of x. And if my point is x plus h, then I have to plug that into my function in for x in order to produce the y-coordinate that corresponds to it. So this will be f of x plus h. Note here the function notation. I have to plug x plus h in fully inside of x in order to obtain the y value for it. Okay, so rise over run, that should be pretty straightforward. How much have I risen between these 2 points? Well, I have risen this distance right here, right? This is the vertical distance that I have risen to go from this point to this point. How can I compute it in terms of the y-coordinates that I already have labeled? Well, this distance here is actually the whole distance between f of x plus h and the x-axis minus this distance. Right? If I take the entire distance and subtract this little beginning bit, then I will have exactly the distance that I want. Pause the video here for a second and persuade yourself that this is indeed the case. F of x plus h minus f of x will give me this actual difference between the two y-coordinate and therefore the rise between the 2 points. So the larger of the y-coordinates minus the smaller of the y-coordinates represents the rise. What about the run? I ran from this point to this point. So horizontally, I have traveled exactly this distance h. Excellent. Now, what do we actually have as another descriptor of the slope of a secant line? We've been talking a lot about how the slope of the secant line represents the average rate of change of a function. So this is important to remember here, because what we want to do next is somehow use this idea and the idea that we've discussed before about moving these 2 points closer and closer together, or which is analogous shrinking this h. So I'm moving these 2 points closer together. I would like h to be as small as possible in order to obtain the slope of the tangent line. So overall, the slope of my tangent line will be equal to the slope of the secant line as this distance h between my 2 points goes towards 0. As these 2 points become infinitely close to each other, my red line will turn from secant into a tangent. Okay? Now, What I have is the slope of a secant line is I already have computed here, and I in fact have a very specific formula that relies only on my function f and the x value where I'm interested in the rate of change to actually compute with. What I need is some kind of notation to represent that this h is growing smaller and smaller until it's essentially zero. And that notation is going to be given to us by limit. So limit, and the condition of the limit is going to be written underneath it. So h goes to 0. What I am taking a limit of, and in this case the slope of a secant line, will go inside. So this function, this what we call difference quotient, will go inside this limit. Now we will have an entire chapter to work with limits and understand how to actually compute with them. But for now, this is the actual expression for the slope of the secant line as h goes to 0, which is then also the slope of the tangent line. In fact, this particular quantity is so important, it has several actual names. First of all, it is the slope of the tangent line because that is in fact how we defined it, but I'm going to write it again here because I'm going to summarize the three most important uses for this particular formula. Secondly, we've started with the average rate of change being computed between 2 points, and we've moved the 2 points close together to now represent the actual rate of change at that point, which means that this corresponds to instantaneous, in the instant, rate of change of the function at that particular point. So of f of x at point x. And this quantity is also what we call the derivative of f of x at point x. And of course, the derivative is what we're going to spend most of this course actually discussing. And we've already gotten a definition for it and an understanding of what it means geometrically and what it means sort of verbally or in terms of various kinds of applications that we're going to use. The notations for the derivative, there are quite a few. We can write f prime of x, or we write df by dx, which means the difference in f in the y values divided by the difference in the x values. And so this form is much closer to the rise over run idea, which is nice to remind yourselves of. That is, in fact, always where the derivative comes from. While we haven't yet developed the notions of how to work with limits, let's attempt a first application towards it. So we're back to our watermelon example being thrown off the Tower of Pisa, and we once again have the exact same function as we worked with before. I've relabeled it as f here simply to match the formula on the previous slide so we don't get confused in the function notation and actually focus on the context. We would like to estimate the watermelon's velocity in 3 seconds. So remember last time, because we didn't have the tools to estimate a velocity at any particular point, we had to decide what 2 points to compute the average in between that will somehow be close to 3. Now that we have some understanding of how can we approach instantaneous rate of change computations, we can think of this example as computing the average between 3 seconds and 3 plus h seconds as this h goes towards 0. So, as on the previous slide, we have that the instantaneous rate of change is equal to the actual instantaneous velocity in this case, which can be computed using the limit and the rise over run formula. So overall, this is actually going to be what the instantaneous velocity is. And what we have, as per last slide, I'm simply going to rewrite the formula here that was derived over there. But again, remember that what we're looking at is the rise in the function over the run in the function. So in our case, the height over the time. And we take the limit as h goes to 0 to represent that we're taking the average of the 2 points that are infinitely close together, essentially right the same point on top of each other. Now, once we have that, again, we haven't learned how to really work with limits yet, so bear with me here a little bit. It takes a lot of practice to deal with just the difference quotient itself, so I wanted to do an example of this as early on as possible. So I'm going to simply actually rewrite this limit, and what I'm going to do is expand this thing on the inside. So what am I interested in? I'm interested about the velocity in 3 seconds, which means that my x here is actually going to be 3. So I can first of all replace my x's with 3 because that is the point of interest for me. Now h is going to remain as it is because I am going to send it off towards 0 right at the very end. What I have to focus on now is actually expanding this inside of the limit right here. So what is f of 3 plus h? Notice that f of x is this value here. So if I have to compute it at 3 plus h, I have to sub in 3 plus h everywhere I see x. So be careful with the function notation here. This is not f of 3 plus h. And in fact, if this happens and then f of 3's cancel and you end up with just h on top, you know you've done something wrong. It should not be that easy. You have to plug in the entirety of 3 plus h in for the variable. So what we have for the first term here is going to be 55 minus 4.9 and then 3 plus h squared. Okay? This is what x used to be, and my x now is 3 plus h. Then I also have minus f of 3. So I have to subtract out, plugging in 3 in for x here. So I have 55 minus 4.9 times 3 squared, all over h. This is going to have quite a bit of algebra that you're going to have to figure out. So open up the brackets, open up these brackets, make sure that the minus affects both of the terms inside. I encourage you to actually go through the calculations here. I'm not going to go through the very tedious and very straightforward algebraic manipulations here. What I'm going to do is write down the final step. What you have at the end is there will be all of the constants on top will cancel out and everything on top will have a factor of h that will cancel with a factor of h on the bottom. And so what we're going to have here in the limit is minus 4.9h minus 4.9 times 6. Okay, I'm leaving it as is. And now, if I'm sending h towards 0, in this expression, that means that I can simply plug in h equals 0 in here. The reason I couldn't do it before is because h was in the denominator. I cannot plug in 0 in the denominator, which is why I had to do some algebraic manipulations in order to avoid that trouble. Now there's no denominator because it got canceled, so I can simply replace h with 0, and this will give me minus 29.4. Remember, we have to come up with units because this is an application question. We actually have to think about what it means. I have the units of f, which were the meters for the height, divided by the units of h, which were the time between 3 seconds and a little bit more than 3 seconds. So meters per second. In fact, if you take a look at this number and the number we computed with the averages last time, you'll notice that they're in fact the same. So our approximation from last time between the average was pretty good, except for, of course, it's still not exact. This is the exact velocity at 3 seconds because we managed to send our average off to be computed between 2 points that are on top of each other. So this is the exact velocity in 3 seconds. Let's take a look at another example that ties together the average rate of change and the instantaneous rate of change and how to interpret them graphically. So what we have here is a hummingbird, and the hummingbird extracts nectar from the flowers or a patch of flowers. As time goes on, it of course gathers more and more nectar, and we can also describe it in terms of the energetic gains in calories increase. Here's the graph that corresponds to one particular flower patch. You will notice the actual shape of the graph is familiar, and it looks kind of like a linear hill function. It also makes sense in the context. At the beginning, when the bird just arrives to the flower patch, there's a lot of nectar to be gathered, and so at the beginning, there is the large increase in the energetic gain as it gets all the sugar from all the flowers. But then the bird slowly sort of ends up running out of flowers that are still available for picking, and the energetic gains actually level off. One of the interesting problems in ecology is this problem of when does an animal have to switch the feeding side in order to optimize the amount of energy gathered, right? If you switch too early, you might take too long of a time to travel between the patches and lose a lot of energy that way. But if you switch too late, you've sort of plateaued and you're not getting enough from the patch that you're on. Okay, so this is another problem that we're going to take a look at later in the course as well. For now, we're asked to approximate the average rate of energy intake over the first minute. So here, time is given to us in seconds. So this is the time that corresponds to 1 minute. So let's first of all decipher what this sentence is all about. The average rate of change. Now, we don't have a formula that we can plug things into. All we have is a graph, which means that we have to interpret this idea graphically. The average rate of change always corresponds to the slope of the secant line. So let's note that so we know what we're looking for, the slope of the secant line. Now, over the first minute means between 0 seconds and 60 seconds. So I'm looking at 2 points on the graph, the 0, 0, and the 60 and whatever the energy is. So let's actually label these points, 0, 0, and 60 seconds, and 1,000 for some units. So let's say 1,000 calories here, okay? So the average rate of change of the calorie intake here, average rate of change, there we go, will be computed as we have always computed it, and in particular, it will correspond to the slope of the secant line, so it has to correspond to the rise over run, or we can also think of that as change in energy over the change in time. This is the sort of verbal description of what we're looking for. The graphical description, which is what we have to compute with, is going to be represented by rise over run. And so be the slope of this secant line right here. So the rise here went from 0 to all the way up here 1,000. I can think of that as 1,000 minus 0, or simply 1,000 divided by the run, which is the time that has passed, which is 60 seconds. So if I calculate that, they will be approximately 16.7. And now I have to think of units. Change in energy. Energy was in calories. So I have calories on top per change in time, and time was measured in seconds. So I have per second. So on this patch, over the first minute, the bird is getting approximately 16.7 calories per second increase. Now, next up is the exact same question, but now we're after the instantaneous rate of change. Again, we don't have a formula, so we cannot do the thing that we just did with the limit calculation. And again, we're not really quite as comfortable with limits yet as we should be before we start using them. But the instantaneous rate of change immediately on the graph corresponds to the slope of the tangent line. And here we're interested at what happens in 10 seconds. So at the point that corresponds to 10 seconds on the graph right here is where I'm interested in the slope of the tangent line. Now, I have no formula to plug it in. All I have to do is the graph. So what I have to do is my best in order to draw the line that is tangent to the curve at that point. So it touches it and mimics the shape of the curve at that point. And then essentially compute the slope of this particular line. The way you do that will be to pick 2 points on this line somewhere. And this is where the real estimate will come through. Your drawn tangent line might not look exactly the same as mine. It better not, because my line was drawn freehand and so will yours. So both of our numbers will be approximations. I encourage you to pause the video here, draw the actual tangent line, pick any 2 points on it, anywhere at all, and compute the slope of it. This will be your approximation of the actual instantaneous rate of intake at 10 seconds. What I will have here is I will label some 2 points that I got on my line. So for example, this point right here, and I will use a rough estimate for it. So let's say I think that this point is in 3 seconds, which isn't that far off, right? If this is 5, this looks approximately like 3. And the reason I picked this point right here is because it actually falls on the 400 grid line. And then the other point, maybe I'll pick this point right here that again falls on the grid line and is just a little bit left off of halfway point between 10 and 20. So let me approximate it as 14 and 800. Okay, now that I have myself 2 points, I can simply compute the slope in between them. You can also use the point that you chose. I didn't really care to use it because it wasn't on one of the grid lines here, and I find that this would be much more difficult to approximate. At least there's only 10 units in this square here. There's 200 units in this square here. So even a very small error will result in being propagated quite a bit through the computations. So what I will have is the slope of the tangent line is then approximately equal to, I have to write approximately because my numbers now are definitely not exact because they're just approximations from the graph. It's going to be rise between these 2 points, so 800 minus 400 divided by the run between these 2 points, so 14 minus 3. So overall I have 400 over 11, which results in approximately 36.3. And again, I'm going to have calories per second. So just to be very clear here, I'm also going to make sure that I actually write this on the graph. These points are approximations. Now, once we have that, we can see that this is the rate of energy intake in 10 seconds. Remember that the previous slide said that the average rate of energy intake is 16 points second. This is quite a bit higher than that, and we can of course see that our previous slide had the secant line that looked like this. This line is quite a bit steeper, so its slope will be higher than the average, and that makes perfect sense. Because notice that in the beginning, the intake is fairly steep, and then it starts leveling off until it becomes really quite slow. So the average will balance out the highs and the lows. Therefore, something in the middle here with a clearly steeper slope will also be bigger in number than the overall average. Now let's take a look at another example that involves an actual function. So in the hummingbird example, we were provided a graphical information and asked to interpret some variant of the average and the instantaneous rate. Here, we're starting with the actual formula. And this formula describes a biomass of a particular type of crayfish, where the biomass is given in grams and X, the variable in the biomass, represents the number of weeks after September 1st. So let's see what we are after here first. First of all, we would like to find the average rate of change of the biomass between weeks 20 and 40 and make sure that we have the unit. And then we're asked to sketch the graph and interpret this information within the graph. So let's get going. First of all, the average rate of change. So recall that the average rate of change is always the change in your actual variable divided by the change in this case, time, because we are asked for a particular time period. So the average rate of change, let's write that down, average rate of change between weeks 20 and 40 will be given to us as before with the formula B of 40 minus B of 20 divided by 40 minus 20. All we have to do here is plug in numbers. So I'm going to plug in 40 into this formula and get a number. I'm going to plug in 20 into this formula and get a number. The overall result should be a number. Once I've plugged everything in and divided, I'm going to notice that I get a negative 240. First up, we are going to think about units, specifically because we're asked to think about units, but also because in essentially all the word problems, it will help guide you in terms of whether or not you're on the right track. So the units are given to us by this fraction right here. The tops were the differences in biomass, which of course are measured in grams. So on top, I have grams. And on the bottom, I have the difference in the time span, difference in weeks. And so on the bottom, I have week, which means that my units are grams per week. So the average rate of change between weeks 20 and 40 is negative 240 grams per week. Negative here means it's decreasing. And that is a very important observation because it doesn't mean that you've done something wrong. So just because you see a negative number in a rate of change, don't just assume that it should have been positive and ignore the minus. The negative means that we are losing the weight of the biomass at the rate of 240 grams per week. So the overall biomass at this point in time is actually decreasing. It might help to indeed sketch the graph to see what the actual picture of the biomass growth looks like. Now, one thing about sketching graphs for such large functions, if we pull up Desmos and you notice that I already have the formula entered and I hit enter, nothing pops up on the graph. And that can be worrisome at first. However, notice that the default scale that Desmos gives me is very small, whereas the numbers in our formula are fairly large. So all we really have to do is zoom out and we will see, there we go, is the red graph of the actual function. Now I'm going to have to zoom out for quite a bit more to really see the shape. And by then, if I'm zooming out uniformly across the x and the y, I'm not going to really get a feel for what the function looks like. We are expecting a downward facing parabola. And what would help really is to actually click on this little wrench and fix the domain and the range that we're looking for. So if we go on x from, let's say, 0 to, 200, it might take us a while to play with the numbers to figure out how big the number should be for us to actually see the graph on a reasonable scale. Well, 200, I already see the graph, so it's below 100, so maybe I will make it up to 100 on x. And for y, I'm going to start with 0, and again, playing around with the numbers. Let's say I enter 10,000, doesn't seem to be big enough. 100,000 seems to get us there, and I actually notice that the graph falls below 60,000, so maybe this is a better scale for y. And once I have that, I can see my nice downward facing parabola shape. So let's copy this over onto our slides. Here it is right there. We have sketched the graph. Again, it's good to establish the expectation, first of all, that this is in fact a parabola because it's a square and it's going to be downward facing because it's negative coefficient in front of x squared. And what do we see now? So what do we notice? Well, we notice that, in fact, the parabola is increasing. It's going upwards, which means that the biomass itself is actually getting larger and larger for the x's in the first 20 weeks. Maybe it's actually good to label our function and our axis here. So this is given to us in weeks, and this is given to us in grams. So we notice that for the first little while, approximately up to here, it's increasing. So the animals, the crayfish, are in fact growing. And then afterwards, the biomass is decreasing. So either they're dying out naturally, or they've acquired a predator, or they grew big enough that the fishermen are actually able to catch them, and so on and so forth, or they're just going through the regular cycles of increased and decreased biomass. Whatever the actual factors are, we notice from the graph that it starts off with an increase and then goes down to decrease. Let's think about what the actual average rate of change here represents. I am looking between weeks 20 and 40. So on the graph, that will correspond to this point here and this point here, right? Again, 20 and 40 are indeed my weeks on the x-axis here. The average rate of change, I'm going to write this down because it's going to come up again and again and is extremely important, is the slope of the secant line. which means that if I draw a line between these 2 points, 20 and 40 on my graph here, okay, I'm doing this by hand and the graph is fairly small, but here's the line. I notice that indeed it is sloped downwards, which confirms the fact that I should get a negative as the value for its slope. Graphical confirmation is always important because it can confirm or deny our calculations, right? Yet another way to check something. So once again, we notice that in the beginning, the biomass is increasing and then it starts decreasing. And in particular, in the weeks 20 to 40, we're seeing a general decrease. If we're wondering about the highest biomass, the graph can be helpful in approximating the highest point. Here it's about 20, but this is just an approximation. This isn't really a definite answer. Okay, let's take a look at the next question. We are moving on from the average to the instantaneous. So in terms of the graph, the instantaneous rate of change will correspond to the slope of tangent line. And we're asked to find that slope of the tangent line in week 1. So based on our graph, let's take a quick look back here. If this is 20, week 1 is going to be really close to 0, so somewhere here. We're looking for a slope of a tangent line at this point. At this point, we are expecting a positive slope, so a positive number as the answer. But of course, now we're not looking for the average, we're looking for instantaneous. So we don't have 2 points to go off of, we only have 1 point in week 1. So what we're going to be looking at is essentially the instantaneous rate of change between 1 and 1 plus h, where h is approaching 0. Now, as I said before, we haven't dealt with limits rigorously yet, so this is something that we're going to learn in more detail in the next unit, but this is our first go at how to work with these units. So I'm going to look at the average between 1 and 1 plus h. According to the exact same formula I've used before, that means I have to plug in 1 plus h into my function b, subtract b at 1 as the value. So this gives me the difference in the biomass that occurred between weeks 1 plus h and week 1. And then I have to divide by the time period between week 1 plus h and week 1. So on the bottom, I'm going to have 1 plus h minus 1. Now on the bottom, of course, I can notice that 1's cancel right away, so I'm only going to have h. And all of this has to happen as h approaches 0. So I'm going to introduce my limit notation here as h approaches 0. And because, again, I'm not yet rigorously involved with limits, I am, for the large part, am going to ignore this limit while I simplify this expression right here. The reason I cannot plug in h equals 0 immediately is because h is in fact a factor, not a factor, a term on the bottom, the only term on the bottom. So I will be dividing by 0 if I just plug in h equals 0. I cannot do that, so the first thing to do is expand the top and then hope that in the simplifications, this problem will somehow go away. Now, this is going to be tedious. I'm going to just keep rewriting limit but not do anything with it. This is going to be tedious because I have to plug 1 plus h in for x into my formula for b of x. Okay, so this is going to be extremely important. This entire factor is going to be my plugging in of the 1 plus h where x goes. So I'm going to have to be extremely careful to actually replace x with the entirety of 1 plus h. Okay, so what I'm going to get is minus 12, 1 plus h, all squared, okay, all squared, not 1 plus h squared. I have to plug in 1 plus h where I see x. I know I am really getting stuck on this point, but this is the mistake that I see most students make here at this stage. So I'm going to really hammer it in that we are plugging in 1 plus h into the entirety of x. Okay, just literally think about it as patching it into there, right? So 1 plus h all squared plus 480 times x, but now my x is replaced with 1 plus h plus 54 54,000. So this entire expression is my B of 1 plus H. Let's put it into its own set of brackets just to be sure that we're actually seeing the distinction here. Minus, and then I have to subtract B of 1. So I'm going to put in another set of big brackets here because I want to make sure that whatever I get from B of 1, the entire thing gets subtracted, so I don't accidentally lose a sign there. But this one is easy. All I do is now plug in 1 in for x, okay? So minus 12 times 1 squared. Well, let me actually write this in. 1 squared plus 480 times 1 plus 54,000. Okay, so this entire expression corresponds to B of 1. Excellent. And this is why I said this is going to be a little bit tedious, because now we have to divide this whole thing out by H, and that means that I have to simplify that entire top and see if maybe I acquire a factor of H to cancel out with the bottom. I encourage you to pause the video here and practice doing this, because we will do this several more times in the limits and the derivative section, okay? Opening up the brackets, making sure you deal carefully with the different signs here and there, and then canceling out as much as you can from the top of this fraction, okay? Take a minute, pause, and actually do that. All right, I'm going to skip the steps of actually opening up the brackets here. This should result in something like 1 squared plus h squared plus 2h. Be careful about opening it up. It's not just the square being applied to both terms. You're actually squaring the bracket. So you will get to FOIL it out and get 4 terms in total, okay? Once you've opened all of this up and you would have canceled some of these things to the similar terms in each bracket, what you should get is minus 24h minus 12h squared plus 480h. Okay, this is sort of like my semi-intermediate step there. Once you just open the brackets and cancel the obvious things out. Notice that the 54,000 and the minus 54,000 got canceled immediately here, so I'm not even seeing this like particular constant term. Now, putting the similar terms that I have left here, minus 24 plus 480, I'm going to have minus 12h squared plus 456h divided by h. And now I notice that the really convenient thing is that h is actually a factor of the top, so I can take it out from the top. Be careful here as well. What I see happen a lot is people cancel these two h's, which is wrong. You can't cancel from just one term on the top. You have to deal with the entire numerator as a whole. So the only thing I can do at this point is actually factor out h from the top, minus 12h plus 456 divided by h, and now that h is a factor of the top, I can actually cancel it out with the bottom h. So what I have left, again, ignoring the limit, but actually rewriting it, so I remember that my h is going towards 0, I have minus 12h plus 456. Now, at this point, though, remembering that h approaches 0, and now I no longer have a denominator because I've managed to cancel it out, I can actually just plug in 0 for h. So if h goes to 0, minus 12h also will go towards 0. And the only term I will have remaining is 456. And what are my units here? Let's take a look at the first expression. On top, we had a difference in biomass, which was measured in grams. And on the bottom, we had the difference in weeks. And that is giving us the units of 456 grams per week. So that means that in week 1, the biomass is actually increasing because the number here is positive. So I can say is increasing, at the rate of 456 grams per week. Again, this is consistent with our observation of the graph actually increasing in week 1. Okay, a lot of calculations, but this is getting to the instantaneous rate of change from the average rate of change in the most direct way possible. Let's take a look at the next one. Find the instantaneous rate of change in week 30. What does this correspond to on the graph? So what we're going to have here is the exact same procedure, but now we're going to be looking between week 30 and 30 plus h. So take a minute here, pause, and try to set up the corresponding limit that will, as the one from the previous slide, but that will actually match to week 30 calculations. So what you should have here is b of 30 plus h minus b of 30, all divided by 30 plus h minus 30. We're going to apply very similar simplifications here. In fact, this entire example is going to be identical to the one on the previous page, except for instead of 1, we have 30 everywhere. Now notice as before that 30 in the bottom cancels immediately. And then the next thing I have to do is plug in 30 plus h everywhere I see x to get the first term, and then minus plug in 30 everywhere I see x to get the second term. Pause the video and actually plug things in for yourself to see how they will go. So what we're going to have here is minus 12, 30 plus h all squared, okay? All squared, not just h squared, 30 plus h all squared, plus 480 times 30 plus h plus 54,000. That is going to be my first term right here, this guy, minus, and then I'm subtracting the term b of 30. So just plugging in 30 in for x will give me minus 12, 30 squared, plus 480 times 30 plus 54,000. All of this divided by h. Okay, again, coming from the fact that the 30s on the bottom actually just got canceled. I am not going to simplify this. I leave it up to you to simplify. If you're struggling with actually opening up the brackets and simplifying this, take a look at the pre-calculus review package for some refresher on how to open up the brackets, do the similar terms, and so on and so forth. So there's a few steps missing here in terms of the actual arithmetic, let's say. And what you should get in the end is a limit of something. The h's will cancel, and so on and so forth. I'm going to skip all of these steps because it will be really excellent practice if you do them yourself. And then the final answer that you should get is minus 240. And in terms of units, we still have grams per week. Okay, so that means that in week 30, the biomass is now decreasing, because it's negative, at the rate of 240 grams per week. Okay, what does this correspond to on the graph? Let's pull up our graph once again here. Here's my graph that I have acquired from Desmos. So on the previous slide, we were calculating the rate of change in week 1, which means that we were actually getting the slope of the tangent line at the point of 1. So if I draw the tangent line here, this is my tangent line from the previous slide, and this corresponded to the slope being 456. Here I am calculating the instantaneous rate of change, which means the slope of the tangent line in week 30. So at point 30, which is halfway between 20 and 40, so this right here. And I notice that if I draw the tangent line here now, it's going to have a negative slope. So this has the slope, as we've just calculated, of minus 240. So our calculations confirm what we see on the graph. At the beginning, the biomass rate is increasing, and after a certain point, which looks like approximately 20 weeks, it starts decreasing. Okay? Once again, the point to remember is that the instantaneous rate of change corresponds to the slope of tangent line at that point. Okay, not just any tangent line, the tangent line at the point where we're actually calculating the slope. And given that, it can be negative, which will signify the decrease. Here, for the positive slope, the biomass is increasing. And for the negative slope here, the biomass is decreasing. In order for us to actually find the precise point where the change occurs, we will have to develop other tools, or in this particular case, because it's a parabola, you can in fact use pre-calculus techniques to find the vertex, which will be the maximum, but we will actually develop calculus techniques to do it in a cleaner and much more efficient way.